So the size of my writing usually tends to 0. So please shout from behind whenever it's badly written. Okay, so I will tell you about systolic growth, and we'll first define what it is in the context of groups. So it comes from some definition by Gromov in a paper, which is proceedings of some conference in the honor of Marcel Berger, from conference from '92, and the paper is about systolic inequalities, and it's typically Riemannian manifolds. It's geometry. There are some fundamental groups, but it's basically it's Riemannian, and there is like a one-page digression about groups. And so at some point by some Google random walk, I came to read this paper. And I saw this paper has had a number of quotations from the side of Riemannian geometry, but this was sort of forgotten, and it's a very nice notion. So the context is gamma, a finitely generated group. And say endowed with a word length with respect to some choice of generating set. And first there is the notion of systole, which has nothing mysterious. If lambda is inside a gamma, say a subgroup, the systole of lambda, it will be sys afterwards, of lambda is the smallest size of a non-trivial element. So geometrically, what is this? If it's the smallest size of a loop, smallest, yes, of a loop in the Cayley graph, say Cayley, modulo lambda, that does not lift. To a loop in gamma, and I should say a loop, it's actually a based loop. So typically systole is the smallest homotopically non-trivial curve in a manifold. In some cases, when typically if lambda is a nice fundamental group of Riemannian manifold with say positively curved, it really corresponds to something, essentially corresponds to the smallest size of a non-trivial loop. Okay, but anyway, that's if you from the combinatorial side, this is the definition. Okay, and this is my object, and this is something which moves. I want to study gamma and to figure out how this systole behaves when we pass to finite index subgroups. Geometrically, it's study the systole of higher and bigger finite covering. So systolic growth is so sigma of n, which depends on gamma and of S on the generating subset. It's the smallest index lambda is a subgroup, and the systole of lambda is greater or equal to n. So it's possibly infinite. Okay, that's the number, and I want to study this as a function of n. And so the first basic remark, so it's non-decreasing function, and when it's really a function, so the first remark, it takes finite values, if and only if.
Is normal or not necessarily?
Not necessarily.
So it's a loop in a Schreier graph, right? It's minimal loop in a Schreier graph.
It's not a. I mod out a Cayley graph. It's not.
It's not. What is Cayley graph? Authorized by lambda. Isn't Schreier graph?
It's a Schreier graph of. You mod out on the left. Yes, it's Schreier graph. Yes, actually, it's Schreier graph. Because you mod out on the left, so it's Schreier graph. Usually, you multiply by elements on the left and you mod out on the right. But here you do both things the other side, so it's fine. So smallest loop based. There is a non-based version, and all of the results will be essentially the same in what I will be talking about. Okay, first remark: if and only if gamma is residually finite. Because this means to say that the systole is greater than n means that I avoid the n ball. So that's a restatement. And the point is that it gives a kind of quantitative way of residual finiteness. There have been quite a few such things that have been developed in the last few years. And the first, so now we'll study for in the residually finite case and compare to some other kind of growth, and the first is the usual growth. So another remark, 1, 2, if b of n is the growth, so cardinal of the n ball, there is the equality, then sigma of 2n plus 1 is greater or equal to b of n. And that's really a remark. That's because if systole of lambda is greater than 2n plus 1, then the ball of radius n, when you map to gamma mod lambda, this is injective. So the cardinal of b of n is less, that's b of n, and that the cardinal here is by definition at least 2n plus 2. Okay. So basically, okay, there is dependency on the choice of S. So the asymptotic behavior of sigma of gamma S only depends on gamma. So asymptotic behavior is the same in the same sense as when you define asymptotic behavior for the growth. So it's when constant occur inside and outside the variable. If you want a precise definition, I will write the inequality, but it's the same as the one used for the growth. For instance, 2 to the n and 3 to the n are equivalent, have the same asymptotic behavior. But 2 to the n to the square, n to the cube do not have the same behavior. So let's say that sigma, it's restated, sigma is at least the growth, and natural question is to wonder what can we say about the growth. Is this an equivalence, or in which case? Examples. Let's start with z to the d. And here we have an inequality saying the systolic growth is at least the growth which is n to the d, and n z to the d has index n to the d and systole n for the standard generating sets. So here that's proof that the systolic growth is at most n to the d, so you get the growth. Second example is SLDZ. Okay. So here, the n ball with any choice of S is I will be a bit sketchy, but the n ball is contained in matrices of at most exponential growth. So for some exponential bound, it's contained in the set of matrices with some exponential bound on n, and this number of such matrices is at most exponential, and so pick P. Actually, I want to say prime because I like primes to reduce modulo primes, but I don't need this, of exponential size, but large enough, so which means greater than the exponential bound, then the n ball will be mapped to the reduction SLD of z mod p is injective. So P equals Pn. So Pn, it's m to the n for m large enough, is injective, and this is of exponential size. So it proves that the growth is at most exponential. And actually, it actually works for any subgroup therein. Not only SLDZ, it gives an exponential bound, and as you know, so for most groups, subgroups here, the group is exactly exponential, and this gives some exponential behavior. And by an obvious variation, also for finitely generated subgroups of SLDQ. Because when you pick a subgroup, you are actually in SLDZ with M inverted, and you can reduce modulo all number co-prime to this, to some given number. So you have enough room to make this reduction. You just have to pick almost all possible Pn. Okay, so it gives an exponential upper bound. Okay, I will go back to this, but I want to say something before I forget it. It can be large. Can be arbitrarily large for suitable finitely generated groups. That's due to Bou-Rabee and Seward And so actually they don't consider this notion, they consider this notion with normal subgroups. But they get a smaller function, and this smaller function could be arbitrarily large. Could be arbitrarily large means every Goring function, every function is asymptotically a lower bound for some systolic growth of some a bit pathologic but residually finite group. So really, in the other side, I want to, when does it behave reasonably for groups that are reasonable? And so what comes after Q is the linear case. And I will keep.
What is the generic set?
It's. I think.
Wait, the board has two sides. But continue.
Yeah, but anyway, you won't see the other side. Oh, unless you want to see it the other side.
How does it depend on generating sets? So
the asymptotic behavior does not depend. So, in the usual sense, with constants inside and outside the variable.
What about quasi-isometric behavior?
It's more residual finiteness is bad, and also even between quasi-isometric between residually finite groups is not so well behaved. But anyway, you have you have groups. I don't know if it's known, but at least you should have some irreducible lattice. If they have congruent subgroup property, they will. No, okay. Let me think of it. Okay, I have to think more. I expect it's bad, and it's just harder when you stick to residual finiteness. But I have to think twice. Okay. So actually, my favorite example of a group which is linear but not over Q is would be, say, the width product of Z with Z. I won't go precisely into this group, so I just write it. But it's an example for which, if you get a naive reduction, you get sigma of n is at most n to the n. If you do like a kind of stupid congruence subgroup argument. And at some point I was really expecting that you get some interesting behavior. Actually, no. So with Bou-Rabee, we proved actually that for every gamma finitely generated linear over a field or product of fields, the sigma of n is at most exponential. So hence, sigma of n is precisely exponential unless gamma is virtually nilpotent. And so we mark on the proof. So you use a counting argument to reduce modulo a suitable, so maximal ideal. So like it's like a prime, but you have to when you have bigger rings, what you want is to find the finite fields that are quotient of this ring. So that's. So when you do this, even in a particular case like Z, wreath product Z, so that's the ring is the Laurent polynomial ring on Z, it makes things really not explicit. It does not mean there is no hope to make it explicit, but the proof is not. It's so that's all I wrote on the proof, because there is one case left, which is the virtually nilpotent case, and I want to. The remainder of the talk will be about the virtually nilpotent case. And a remark I should have said for the beginning, sigma decreases in a large sense, decreases when passing to finite, to subgroups, and it does not change up to asymptotic behavior when passing to a given finite index subgroup. The systolic growth of a group or finite index subgroup is the same. So you can drop the word virtually and get to the nilpotent case. And that's really something, if you do it with the normal one, you get a problem, because normal subgroup of the finite index subgroup, quotients of the finite index subgroup are not quotients, and you get a kind of there's some power that comes, and so that's really not true. Not necessarily true when for the normal version. Okay, so in the nilpotent case, from what I said, I have for the moment an exponential bound, because I told you it's linear, and we have an exponential graph. It's even easy because it's linear over Z. So by an easy argument, you have an exponential bound. But in the nilpotent case, it's actually the same argument gives a polynomial bound, because when you take the n ball and the group is written as a virtually unipotent group, then the n ball has elements of polynomial size and not exponential. So the same argument can be done to get a bad but polynomial bound. And so that's a way to get an extremely bad bound, and we can get some using kind of congruent subgroups inside the group. There is a way to get something not as completely out of control, but something which is still usually not optimal. So I should say one example. Actually, that's basically the only example that occurs in this Gromov paper. So Heisenberg group. If I take the integral Heisenberg group, then you consider lambda n as the set of matrices of the form 1 nx, 1 1 ny, n, and here n square z. And just as a kind of witness of the argument, let me say gamma prime n the same with nz instead of n square z. So that's the congruent subgroup. This one is not, but this is a subgroup because the computation makes a square when you multiply this and this. So gamma n, lambda n, its index. Index for lambda n, lambda prime n. The index is here n squared makes n to the 4. And prime n, oh wow, it's better because I have n, so I get n3. So probably this was a better choice. But if I look at what's the systole of this, the point is that nz, the matrix 1, 1, 1, 0, 0, such a matrix has size essentially square root of z. So if you have the matrix 1, 1, 1, 0, 0, n, it has square root of n size. And basically that's the thing to retain. So this systole here is square root of n, and here, but here it's done so that it behaves better. So that's n. So all these are about. So what we get here from this, we get that sigma n is at most n4, and from this what we get is only sigma of n is at most n6 from square root to n cube. So this was not just a lack of time, because if you consider only normal subgroups, this subgroup is not normal. This is congruent subgroup, it's normal. So actually it's sharp. You get the normal one is n to the 6. And here we are done because we know that the growth of the Heisenberg group is n to the 4, because the n ball essentially contains all integers from minus n to n here, minus n to n here, and minus n squared to n squared here. So that's n to the 4 elements, which is the growth of H3. Okay, so that's okay with this example. And so one question is when is sigma for a nilpotent group, when is it equivalent to the growth? And in this gram of paper, he said, oh, it's a sentence. It's when the Lie algebra is graded. And so my remainder of the talk will be about this. To explain, I want to explain exactly what it means. And yes, I will erase this. Or maybe I should really erase. I don't know if I should keep the. It's. I think I should really. I think I really want to keep this. So. I will. Okay, theorem. So equivalence between two statements. One, gamma. So let gamma be a finitely generated nilpotent group. Let's say torsion free. One, sigma for gamma of n is equivalent to the growth. And two, that's what I call graded, but graded is quite bad, so I will say the Malcev Lie algebra of gamma is Carnot. And
is it equally to think that the group admits a homotopy?
Yes. Probably that's. I'm not sure what you mean, but probably it means this. So, no, but I mean, okay. Yeah. Will you explain? Yes, I will explain what I mean by this. It's part of the plan. So first I remind what Malcev is. Malcev proves that if gamma is...
You should write it with double F.
So I will be a bit imprecise, but that will be enough. There exists U, a unipotent Q group, and a homomorphism from gamma to U of Q, which is an injective homomorphism such that also gamma maps gamma to a lattice. U of R is a simply connected Lie group. So U, if K is a field of characteristic 0, a U of K is the Malcev K completion of gamma. So it's essentially unique. So I would say unique without being precise. And it's Lie algebra called little u of k, which is also isomorphic to little u of q tensored with k, is the Malcev Lie algebra of gamma over k. So usually what's mostly interesting is Q, R, and possibly C, because C is quite natural. And there are more further properties. For instance, gamma intersects in U of Q, and only in U of Q, gamma intersects every non-trivial subgroup. That's kind of envelope characterization. How much time do I have?
So you said about 7 minutes.
7 minutes. Okay, that's one definition. Second definition is Lie algebra over a field K is Carnot. Is Carnot graded if endowed with grading G equals the sum of G I belongs to, say, Z. Graded means that GI, GJ belong contained in GI plus J, and Carnot means that G is generated by G1. So in particular, there are only, it's a positive grading. And G is say Carnot gradable, say over K, if it admits such a grading. So to be correct, say Carnot gradable. And here I was imprecise because I didn't say what's graded over Q over R. So let's say over which direction? Over Q and 3 or 2A. Same thing over the reals. Okay, so I will say quickly a words about all of these equivalences. And so we already erase this. I should mention that passing from Q to R is obvious because you tensor and you get the grading. There is some point in some algebraic fact from going to 2B to 2-1, which you really need in the proof, and that's purely algebraic thing. And the way you define a Carnot grading, it does not make it obvious. But now there is a way to make it clear, is that G has a Carnot grading, is Carnot gradable, if and only if there exists D from G to G, a derivation such that D induces identity on the abelianization. So if G is Carnot, take D of D respective to Gi is the multiplication by I, and there is a converse in characteristic 0, which is not hard. And if you're familiar with such a condition, is really it's an affine. It says that some affine space has a point, and that does not depend on the field. So it's basic algebra. But anyway, there's. I mean, it's a new result which appeared in a paper about 15 years ago, but with a false proof. So, I mean, definitely false proof. Based on the idea that if you have a Carnot graded Lie algebra, any supplement subspace of GG can be made G1. And that's not true.
Algebra is not assumed to be finitely dimensional?
Yes. I don't know if it's true in a characteristic P when the dimension is large compared to P. Okay. So 2A implies 1. It's essentially you have to mimic the Heisenberg, which is erased. So basically, you use the idea that's a derivation. You multiply by I on Gi. When you exponentiate, it means you can multiply by say 2 to the I on Gi, and you want to pass this to gamma, and possibly you cannot, but some large power will pass to gamma. We'll map gamma into gamma. I cheat a little, but that's essentially this. The issue is that gamma can be some, not exactly the integral points, but some bad subgroup of finite index. But okay. And the main implication is the one implies 2b, and how much time do I have? I have 2 minutes or? Okay. So I have my gamma, and I map it into, say, U of R, which I call this G. So it's a lattice. And inside, I have subgroups gamma n, say of C. I cheat a little, but it does not change the proof. Systole is about n, and the index is about n to the d, where d is a growth. It's the growth of gamma n of g, the volume growth. So what you do is you rescale. Okay, I should say delta because I want to write the distance. So I endow g with a distance, Riemannian distance, and I rescale. I have a group which is now the same group, but which is rescaled at each step. The systole is now about 1. Okay, index, I don't care. The systole is now about 1, and now I use this sequence of spaces, which is by Pensu theorem. It converges to some G infinity, which is a Carnot group. And now you have a sequence of subgroups. So you can obviously, up to extract, you can make it converge to something. Okay, I put gamma infinity. And the first point, so gamma infinity is a subgroup. It's not completely obvious because this limiting process does not make it clear that it's canonically a group. But for these groups, you can check that it's canonically a group in such a way that it's obvious that it's a subgroup. So that's really some point. Second, okay, it's obviously discrete because the systole was 1. But now you have to keep in mind that typically we want this to be a lattice. And if you are in Z square and you take say nz cross square root of nz, and you rescale by the systole, what you get at the limit will be z, because when you rescale, you get square root of nz cross z, and this tends to z as a subgroup of z square. I mean, as the subgroup of R square. So there is a point to show that gamma infinity is a lattice, and that's really where the index assumption is used. It's it's based on some kind of uniform generation that gamma n is generated by its Cn ball in some uniformly efficient way, and from this passes to the limit, and then you get that gamma n tends to gamma infinity, not only in this Gromov-Hausdorff sense, but as marked groups, which is much stronger. And now the point is that the dimension of G is equal to the dimension of G infinity. That's part of Pensu's constructions. It means that there is a kind of we will keep track of G, and they have the same Hirsch length. But also, this is nilpotent. So when you converge as marked group, it means that eventually gamma n is a quotient of gamma infinity. But these are nilpotent groups torsion free of the same Hirsch length. So what you show that is that gamma n is isomorphic to gamma infinity for large n. And now you have Malcev rigidity, which says you have two groups, this one and this one, have isomorphic lattices. Implies G is isomorphic to G infinity, and G infinity is Carnot. So G is Carnot over the reals, definitely by Consus theorem. So that's how we get this. So that was really summarized, and I think I know. So one open question is to when it's not Carnot, to you have in some particular cases. So the smallest non-Carnot Lie algebra that are nilpotent are 5-dimensional, so they are quite handy. And so sometimes there is a kind of it gives a lower bound which is strict, like n to the I'm not sure n to the 10, and you have an upper bound which is n to the 11 by some simple construction. And I don't know for any example anything explicit for a precise behavior of systolic growth in the non-Carnot case. Thank you.
Can the chemicals have similar regulatory groups? Have similar regulatory groups, especially of exponential growth? Is it be exponential or not?
I have not checked. I guess. I mean, you have kind of congruence.
The chemicals have the minimum. If it is a similar regulatory group, say sub-exponential growth, and is it finite? So what happens to this? What is this? If you like growth, or if you see something new?
At least I guess it's accessible because there is a good understanding, but I'm not sure.
You have these books in your public, like you.
Well, for the normal version, it's exponential for the Borchardt group. The other function which quantitatively measures.
But normal exponential, you say, yeah?
This is exponential, yeah, but this I don't know.
If you just iterate, you take this simulation.
Yeah.
Multiple, say what happens.
Yeah. This was computed by Bou-Rabee, I think, one of his papers.
So there is no sub-exponential example.
No, I think not.
So that's the question. If there are other sub-exponential examples, except you can do it.
I mean, for you, I don't know.
I never did. I mean, I don't know enough, and I think it's accessible, but not really for me.
In this nilpotent non-Carnot, do you know at least that the exponent is integral?
No. I said I have an example, maybe achieved by one integer, but there is one example where I have some kind of explicit construction, like it's the growth is n to the 10, and I have a bound by n to the 11, and I don't know if it's optimal. Integral would I would guess that integral is actually I don't. I think that's no. I would guess that there are cases where it's fractional. But I guess I would guess that it's always fractional. Because basically, because of okay, you remember the Heisenberg group? I had some square root, and basically, in the cases I checked, you multiply by n to the something on some direction, and what you get eventually should naturally be rational. And I think that I even tried at some point to show that for something I conjecture it's I don't think, but some integer plus 1/2. So my guess is that it's always n to the sum rational. It's maybe too optimistic.
Do you already know that it's n to the something? Can it oscillate between n to the 10 and to the 11? Or?
I would be really surprised.
Okay, last time.